Are you ready?
Yes.
Okay, we can start with Mr. Professor Elfrgani.
Okay. So this part is kind of continuing what I was describing in the lecture before lunch. Basically, in order to understand what's the pi mode, 2 pi mode, and what's the corresponding electromagnetic modes, you need to study or to understand the dispersion characteristics, dispersion relation. So I will start with just general periodic structure, and I will go write you kind of couple of related equations to. I'm not driving anything because it doesn't make sense for this context to drive equations, but I'm gonna write the key equations that describe the dispersion characteristics for different structures. So what you see here is basically similar what I was showing in the morning, that if you can understand and write the fields for rigid waveguide, which is basically two parallel plates, one of them has corrugation and the other one does not have corrugation, and we call this cathode, we call this the anode, and this structure is basically just assuming that it's going to infinity from all directions. But if you twist it around one of these axes, if you bend it, as I was describing in the morning, if you have bent it in this direction, now you came up with this structure, magnetron type structure. If you bend it with a different direction, with different coordinate system, you end up with this structure. Now, you can do the same idea if you remove the smooth conductor here. You can remove it. It's really a jump to write wave equations, fields in these structures without knowing the smooth wall waveguide, fast waves. So let's go ahead and write or show at least the equations for smooth wall, parallel plate, or coaxial direction line, and then get the dispersion curve, and then move from there to show the dispersion characteristic for periodic structure. So I'll switch to, let me see. I'll switch to the writing next to this. And one thing that you need to add to the recipe is the electron beam. Once you add the electron beam, this is no longer as a cold structure. You're going to end up with a coupled structure, and the fields are coupled. And this way makes the equations more complicated.
So it's
hot analysis, but they usually call beam wave coupled dispersion. Right. Yeah, yes, but it's hot analysis. Okay, so let me share the tablet and probably. Did I? Okay, sounds good. Let me just get my notes from here. So don't, I'm not mixing equations and. Okay, so first thing I will do is, I'm not writing everything because this is like well known in textbooks, but just to give you like basic description, I will start off with the parallel plate. Waveguide. So basically you have a parallel plate, waveguide, And this is very basic. I'm not going to do all the math behind it, but the idea is if you use this as a transmission line, is slightly different than what we use in the context of generation. But let's, have something connected to the background or the basics that you know. If you have this parallel plate, can you inject or can you use any source to propagate microwave or an RF between these plates, or do you have some restrictions? Do you guys think any frequency can propagate or not?
This structure has TEM modes, so
Yes.
this cutoff frequency is 0.
Yes. So starting from 0,
Yeah.
you can have
Yeah.
you can have a source and you can send TEM wave. And if you continue increasing the frequency, there is higher order mode will appear, TE or TM. Okay. And again, if we go ahead and twist these waveguides, we're going to end up with the coaxial dimension like this. So this is coaxial line. And for coaxial line, again, we call both of them two-conductor transmission line. Two-conductor transmission line will allow you to start from 0, TEM, and once you increase the frequency, you're going to excite higher order modes. That's basic, and that the field distribution is really not difficult to follow. Now, let's assume that we are connecting these two plates somehow. This is a wall, this is a wall. Now we call it one conductor type of transmission line. Now we add one conductor, and if we do the same thing by removing this inner one, now we have one conductor transmission line. For this type one conductor transmission line, we are no longer can start from 0. We have to have a cutoff. And the first mode is not TEM. We're going to have either TE or TM. Okay. Now, for TEM mode, usually you have, I'm going to use K as a wave number. Hope you guys remember these samples. Always we're going to have K equals omega over C. And beta is always omega over velocity. For TEM, K is always equals omega. K always equals beta. Beta is phase constant. K is the wave number. Now for higher order modes, beta is not going to be equal K, but you're going to have another wave number we call cutoff wave number. So you have to get cutoff wave number first, and then to get the phase constant. But K is always omega over C. Okay, so this is the way you think about it, regardless of the structure, is it rectangular or circular. Now, if you have a rectangular waveguide, calculating cutoff wave number is going to be different than calculating cutoff wave number for circular waveguide. And you guys have seen this in terms of the Bessel function representation of the fields here, sinusoidal sine cosine representation, but always in the direction of propagation, we use exponential function with the complex exponent. And for other coordinate, when you have a standing wave, if you're talking about X and Y, now you have to describe them with the sine and cosine. Sine and cosine describes standing wave. Exponential function with complex exponent is the traveling wave. This is the way you look at the problem. Now you have this relation here. This is what we call dispersion relation. Okay, and how to plot this? It's basically, if you plot, let me remove part of this line. Hopefully I can do it. Oh, it's all gone. If you have the curve, which is basically dispersion curve, is beta omega. And the beta omega, and you can have different way of writing this, is nothing but we are trying to find the relation between the temporal component of the fields and the spatial component of the fields, if we assume the direction of propagation z direction. So we are trying to see what's the relation between those two terms. For TEM, the ratio is always speed of light. So you're going to have a linear, and this is c, basically omega over beta equals c, and this is the phase velocity. When we say c is actually c is the speed of light in the media, right? If you have different media, you're going to have different c, but we are vacuum electron devices, it's vacuum. Good. We don't have epsilon r to bug us all the time. That's good. Now, this is for TEM mode. For either TE or TM modes, you're gonna have cutoff. We talked about cutoff frequency, right? And then you're gonna have this behavior for higher order modes. These are fast waves. The phase velocity the phase velocity is basically the ratio of omega over, at this point, omega over beta is always greater than speed of light, phase velocity. And I can have a ray representation for this in order to get you like a perspective, like always, once you learn physics and you'll say like speed of light is the limit, right? But here is the perspective. It's not actual phase velocity, it's actually greater than speed of light, but it's the perspective that we are taking here. For any case, now we talked about temporal and spatial components, right? It's actually both of them, they are having a sinusoidal behavior and they have a periodicity, kind of a periodicity, right? So here in the temporal component, if this is the field and this is time, this is basically the time period, right? What is if this is beta or z, or maybe beta z? If this is a, what's the periodicity of this spatial component in bounded media? Like one, if here we have a signal going here, what is this periodicity?
Lambda.
Yeah, but what lambda?
P lambda or lambda.
Yeah, so this is lambda, but it is not free space lambda.
Lambda guide.
Yeah, lambda guide is gonna be this one.
Guided guide.
Yeah, because we are talking about guide. So this is what's the what's gonna make a huge difference. Lambda equals lambda guide. I'll come back to this, but
Phase velocity divided by frequency.
yes. So okay. So since you talked about this, let me maybe write the dispersion curve in other formats, basically as the beta is always omega over phase velocity. K, don't even think about this, doesn't change with the mode, but K wave number is going to be cutoff frequency, which is this frequency here, over C. This is another way of writing dispersion curve. We can also write it in terms of the lambda guide. This is basically the dispersion curve, dispersion relation. And dispersion relation is really starting from here. You have seen it in waveguide, smooth wall waveguide. Once we have corrugations, you need to add more to the your recipe. So that means if you have a cutoff, that means each single mode is going to have some stop band and pass band, right? In a smooth wall waveguide, we have this for first mode, we have this. This is the stop band. And pass band is going to be any frequency above that. But close to the omega CO, which is the cutoff frequency, you will really have the slope here is really zero, right? You have a zero slope. What's the slope in this case is basically the group velocity. As you go away from here, your slope is going to be changing, and this is positive slope, and this is your group velocity. And the group velocity is the information is going to be slower than speed of light, but the velocity here at each point, the phase velocity is a greater than speed of light. Now, maybe I can add one thing is basically the cutoff frequency or cutoff wave number, which is I always think about it as the geometry related. It's related to the geometry, right? So the cutoff wave number, maybe for a rectangular waveguide, let's say the fundamental mode or rectangular waveguide, can be given as, everyone have seen this. And for the maybe fundamental circular waveguide, some Bessel function, roots of Bessel function or derivative, right? And for these cases, we have beta does not equal k. This is need to be remember all the time. So now if we go back to the dispersion curve and we examine two frequencies, let's have one frequency here, maybe or more. One, this is F, let's say F1, and this is, let me be consistent with my notes, so I'm not going to be. So maybe 3 points, this is F1, F2, F3. So if we have a parallel plate or maybe rectangular waveguide or even circular waveguide, we can think about this in the terms of ray theory, that is, if the frequency F1, now frequency F1 is greater than F2 and greater than F3. If F1, we are injecting F1 here, you will see that you're going to have a maximum or minimum and then maximum. And this is the wave is propagating this direction, right? Bouncing back and forth between the walls. If you check the velocity of this ray is always in this direction is c. But the collective velocity in this direction is greater than speed of light, which is the phase velocity. If you use the ray representation, you will see how we think about the phase velocity is greater than, maybe I use phase velocity v, phase. If we increase the frequency or decrease the frequency instead, let's go to F3, your ray representation will be like this. So the wave will be going even sharper. If you increase or decrease more closer to this point, which is the cutoff, what's going to happen, you will end up with having waves bouncing to the walls. And this is the evanescent mode or cutoff mode. Okay? The distance here, we continue here, the distance between the maxima or the minimum, this distance is lambda guide. Okay, so this is good enough. Now I can move more toward the slow wave structures and the field representation for that. So let me go ahead and switch back to the PowerPoints Yeah, don't move anything from here. Okay, so now what you saw is basically what we call fast waves. Electromagnetic are fast waves, and they are like, written in terms of electric field, magnetic field. And when you introduce these obstacles, like these boundaries, what's gonna happen, since this is a periodic structure, the fields will be periodic. And the wave number that I was describing, the wave number that related to the dispersion curve will be periodic. And there is a Floquet's theorem or Bloch's theorem in the optics that governs this. So it's basically you write them in terms of Fourier expansion, the fields. So no longer is going to be a simple fields. Now for this structure, this is a cold structure, you have two regions. This region, you can write your fields as you have in a smooth wall waveguide, but you have this second region that you need to write them in terms of the periodic structure. Look, the fields are really complicated. And now what you want to do to find the dispersion relation, this is the whole goal, because we agreed that we need to do the dispersion engineering. What you're going to do, you're going to have to match your boundary conditions here. And these are the boundary conditions that you'll have at x equals 0. Here you have a conductive material, right? You have conductive material, the fields in the conductor is 0. It's going to force the tangential components here to be 0, but the fields here, you need to match them. So basically you're going to have electric field. I'm just writing two components here, but other component might exist. And imagine if we are solving this in a cylindrical coordinate. It's going to be Bessel function. It's going to be a mess. That's why we do it in rectangular geometry, parallel plate, to get like a sense out of that. But once we have a more complicated structure, we use computational tools to get us dispersion characteristics. Okay, so these are two regions, and now we have the equations for two regions with the boundary conditions, and this is what we do, applied electromagnetic. Maxwell's equations, you get wave equations out of that, and then apply boundary conditions, initial conditions, and all of that will give you some solutions that you are trying to find. So now this is the dispersion curve or a dispersion relation for all modes and for all what they call harmonics, basically. So since you are talking about Fourier expansion, you have harmonics because the summation, right? And this is going to be like 0th harmonic or -1 harmonic or so on and so forth. And these are different modes. One of these modes will be resonant with the electron beam. One of them. You're gonna choose one of them in design, Okay, so this is the kind of a little bit of theory. This is another page that. So now, if you add your electron beam here, like if you add your electron beam, now you need to divide your region into 3 regions: region 1, region 2, region 3. And when you match your boundary conditions here, you need to consider the charges. Now, remember the boundary condition, you can have the flux density difference is equals to surface charge or volume charge. And you can't have a volume charge, it's going to be so difficult. So we assume that this electron beam is very thin. So it's only surface charge that will be considered. All of these approximations, and still the solution is going to be really challenging. And now you write your fields in all of these 3 regions and match the boundary conditions. Here we go. And these are boundary conditions. you get like very complicated dispersion curve, dispersion relation. Do we do that every time we design source? We never do that. We just learn it first time, we get a feeling out of that, but then you need to use computational tools because this is very time consuming and doesn't make sense to do it all the time. Yeah, so now you can start designing your source. Since you know the dispersion curve, you will find the interaction point. Let me jump toward, these are, I say, toward this. This is basically the dispersion curve for the slow wave structure. These are the dispersion curves for the smooth wall waveguide. Okay, so basically you're gonna end up with coupling these. This is very not very clear, but you are coupling these curves together, and you end up with the, yeah, here's the figure, very nice one. You end up with these pass bands and stop bands. Okay. Now at certain point here, since this is beta, we can multiply it by the period, and then you can have a phase shift between cavity to cavity. And this is what you see here. It's basically pi mode is beta L. L is the period of the slow wave structure. Okay. So this is very, very difficult topic, to be honest, and it's not straightforward, but it's very important. I think we need the batteries for this. Need batteries? It doesn't. It doesn't show
The same concepts are there in condensed matter physics, optics, always the Dispersion relation, it's always there.
Yeah.
So it's very similar.
Very similar, yes. Yes, they use block theory.
Block theory, I mean,
Yeah.
solid state physics is
Yes.
very same.
Yeah, but
The only thing is the dimensions change. Otherwise, the theory is the same.
Yes.
Zone, crystal is also same.
here we think about it as a periodic structure in one dimension, because we have the beam going in one streaming, and one of the components is gonna interact. And optics probably like 2D.
Yes, usually, yes.
Yeah, or maybe 3D. Yeah, so it's more complicated in some sense. Yeah, but the concept is the same. It's the omega beta curve. So I don't think there's a lot things are repeated here. So I need to jump to the backward wave oscillator presentation. Good.
What's a good reference for this? Especially, the dispersion relation and topics, just discussed.
So there is a Simring book, is a Russian scientist, has like all beam dynamic part and then slow wave structure. But most of the textbooks are really old. There is a Hatter, huh? Yeah. Really? Oh, Brilliant book is very difficult. If you give it to students, nobody will continue this field.
What is the name of the Russian?
Simring book, TSIMRNG, I think. I can send you the name if you want. I think I have it even. Yeah, it's very, very.
If you have a reference list, that will be useful for us.
Okay, for sure. Yeah, I can send. So let me, before I move on to the next, I just wanna show you. So these are the harmonics I was talking about. Usually the interaction either with the 0th harmonic here for first passband or -1 harmonic. I will explain that once we're talking about sources. For magnetrons, it's the same idea, right? It's the same idea. It's basically you can get the dispersion curve with the similar, behavior. And then you can get points. Now, when you have a software, let's show you like magic software. What we do to get the dispersion curve, we have the structure, and then we ping the structure. We send like impulse basically to see what frequency will resonate. Impulse in time domain or frequencies, ideally, right? And we'll see what's going to happen to these frequencies, and starting and give it enough time, and you're going to end up with having these resonance peaks. This is in computer simulation. This is if you have a whole structure and you want to get the points. Remember from the morning we said for linear devices, how many resonance you're going to end up with?
By 2 magnetron.
Yeah, for magnetron. Yeah, for linear devices is n+1, right? So for linear devices n+1, you'll see that there is this first passband, and then second passband, and then so on and so forth. And you can get these points, you know, and get the dispersion curve out of these points. But the problem is not like that easy, because once you have resonances, you have to go at each single resonance and run your eigenmode solver and check the mode pattern. So that's why I have one of the slides here showing the circular waveguide mode pattern. You need to take a look at the mode pattern and make sure that the mode pattern belongs to the passband that you are doing. So this task is really not easy, you know. There is another way, which is kind of ideal way. In CST, we do periodic boundary conditions. We assume the structure is infinitely periodic to both sides, and then get the smooth curve. That's giving you like ideal. It's not the, you know, the actual dispersion curve, but good enough at least. This is in simulation, right? And then this is the next step, is like eigenmode. In experiment, let me.
May I ask a question?
Yeah.
So in CST eigenmode solver, if you apply, for example, 10 modes, then we have to classify these modes by looking for the modes electrically.
Yeah, the mode pattern, yes. Yeah. On CST, if you have one period, it's going to do it for you automatically. It's going to give you like the first mode. You need but just to take a look at the, you know, at the mode pattern maybe once.
We don't use any modes, just like run simulation.
Yeah.
And
yes,
we
I
can see all modes.
Yeah.
Then we need to classify.
Yes. So eigenmode solver is basically all possible solutions, right?
Yes.
Yeah. So it's not like we aren't exciting the structure,
Yes.
but here you have to send a ping function. So it's slightly different strategy. Let me show you the call test. I showed you the equation theoretical model, kind of. It's not, you know, easy to follow, but hopefully you guys remember that very long equation. And I showed you at least give you a sense how to do it using computer simulation. Now, the third step is like you want to verify your dispersion curve in the lab. You have the structure, you want to verify it. How to do that? It's basically, it depends on the mode, of course, right? This is slow wave structure that we need to study as a backward wave oscillator, which is TM01 mode. TM01 mode can be excited by only probe antenna. If you have a probe, lambda over 4, you know, then the current will go through the probe, and then the magnetic field will be circulating like this, and this is basically the TM01 mode. So it's kind of relatively easy to get. So once you have the mode on both sides, you can measure S21 or S11, and you end up with having resonances. Again, how many resonances? Is going to be ideally n+1. And this is the experiment we were doing. But if you go with this simple mode launcher, we call it mode launcher, you will end up with having less resonant points, especially the points at 0 mode and pi mode. The edges are not so clear. Okay, and then you're gonna have these resonances. You follow these resonances and plot your dispersion curve from 0 to 100 80, which is 0 to pi. Okay, and this is another structure that we launched TE11 for different purpose. But if you wanna have maybe all the resonant points to construct your dispersion curve, you need to have more like complicated type of mood launcher, and these are the different ways people have chosen to excite TM01 and then to get the resonances, and from resonances we construct the dispersion curve. And the dispersion curve, I talked at the beginning that since the fields are periodic, wave numbers are periodic, dispersion curve is periodic, right? So it's basically we get the first brilliant zone, this zone, we get this zone, and then we repeat it. That's it. We get this from 0 to pi. This is what we are measuring and simulating and calculating everything. And then we repeat this, and you saw the whole dispersion curve for the different zones. Now this experiment is basically for E-band BWO. E-band is around 78 gigahertz for this one. E-band is 60 to 90, right? This is very high frequency, millimeter wave BWO. And we have designed millimeter wave BWO. We have 3D printed copper plating, and we have tested with the high voltage. And also we have machined it to compare. So before doing the hot test, we call it hot test with the beam, we did cold test, obviously, to check the dispersion curve. And this is the dispersion curve. So we have, since the high frequency, you need to have a waveguide excitation to connect to the VNA. This is the experiment. This part is the slow wave structure, the periodic structure for E-band BWO. It's very small. Now E-band is what? Is 4 millimeter probably, or maybe less. 4 millimeter period. The period of this is lambda. So the period is lambda over 2. So 2 millimeter period basically. Around lambda over 2 is not exact. So look, this is the first passband, second passband. If you can take a look at the VNA measurements. Yeah, again, yeah, getting these S11 and S21. Again, like you see here, we have had some drift tube. We don't want to have your probe, exciting in the slow wave structure because there is a possibility that we're gonna have a huge reflection. So we had to have some small drift tube, probably a couple of lambda length, and we excite this with the TM01, TM02, TM03. This structure is overmoded, TM03, because the higher frequency, you're gonna get smaller cross section. So we had to have TM03 operation of this diamond. Yeah, so from these peaks, we construct our dispersion curve. This first part, and then we repeated this and compare it with the CST simulation. So these are the measurements for both, for the 3D printed and for machined, the same structure. It's very similar, but it's not easy to compare. It's really sensitive. If you just like leave it and the cable will start like bending a little bit, you're gonna excite different modes. It's really like hard to do that. Yeah.
So how do you raise these machines?
This machine is just like the CNC cutting. They have a solid piece and they cut the slow wave structure. Yeah. So they come up with the solid machine. The problem is with the 3D printing. 3D printing is plastic, this one, and then copper plated, electroplating. And once we have it, high voltage and under vacuum, we start losing this copper plating, But we had a couple of shots. We did like a small study, and then we lost it. Now it's on the shelf now. Nowadays is like metal 3D printing is really advancing.
Yeah, 3D printing with the metal,
Yeah, metal. Yeah, it's have high precision.
but still, you see, you don't get the kind of finish which you require, so you have to finish it
Yeah.
again.
Yes, and look, this is like very like critical, very small corrugations, you know. So
What is the surface finishing, you know, the RMS value of surface finishing?
yeah, we measured that for this. We measured that. I don't remember. I have a couple of slides. Maybe I can find for you. Yeah, that is not so great. It's good for
Now,
experiment.
what is the required one, you know, for good performance?
Oh,
What is required surface finishing,
Yeah, so
surface roughness?
softness enough. Yeah. So basically now like we're talking about maybe 2 millimeter lambda over 2, right? So we always for simulation we do like lambda over 10.
Lambda over 10.
Yeah. So this is the rough like approximation. So lambda over 10 probably for machining is possible, but for 3D printing is really challenging, right? Yeah. So it's basically similar. We will like in real life, you need to pay more money to get like a higher precision, but for lab testing, just compromise between like cost and accuracy, right? Okay, this is the dispersion curve. Now we have everything tested in cold test. We're ready to have hot test to put it under, you know, vacuum, high voltage experiment. But the problem is not like, okay, just have your source and start firing and collect data. How to collect data? Diagnostic is a whole field. You need like to work weeks, maybe, or months to calibrate your diagnostic setup. So do all of these steps. So here we have all the receiving equipment shielded because we are radiating high power, and we are radiating very high frequency, 78 gigahertz. We don't have an oscilloscope. I don't think there is an oscilloscope can capture that high frequency. So you need to do what you learned in undergrad, heterodyning. Have a mixer and cosine. Remember trig functions, trig geometry, and then you take the difference and then down conversion. Yeah. So you need to do like down conversion for frequency. And this is what you do for down conversion. You have a lot of components, and these components are semiconductor, low power. So you need to attenuate the signal so hard because we're talking about megawatt of power incoming, and your local oscillator is what, microwatts. So if you have like a lot, even if you have watts coming from one side and you have microwatt, you're not gonna have a balanced mixer. You know, you're not gonna have a difference. One of them is gonna just, you know, you're gonna receive only one of them. The other one is gonna be noise. So you need to attenuate your high power signal a lot. So you need to have, we have like a foam in the front here. And then once the waveguide pick the signal, we have another attenuator, and everything is like need to be shielded. So we put it in the box, we shielding it, and these are the waveguide that picking the signal for voltage measurement, power measurement, and for frequency measurement. And if you take a look, this is your our gun oscillator. So gun oscillator is basically around 78 or 79. So the difference will be a couple of gigahertz that we can measure. So I think I showed you this neon bulb array. We set up our first diagnostic that we make sure that we are radiating power, radiating the right mode. We put the neon bulb array here, and we shoot our pulses, and we capture this in open charm camera to see. I actually have one of the one of the videos that I got on my iPhone, like when I was hiding behind the wall. So that, because look, we have a high energy electrons. And high energy electrons, do you see this? This is lead bricks. You need to shield it. High energy electrons will hit the walls and send X-rays. It's going to radiate X-ray. you know, and it's not high energy, but could be like dangerous for a human. So when we have an experiment, we set up everything and we go to the screen room, Faraday cage. We run the experiment from the safe spot, and everything is shielded here. And this is the antenna that we used. Again, everything here is shielded, and this is the down conversion that we did. Again, like these are all slides that describes the calibration of this. Before you do your experiment, you go to your lab and use VNA to calibrate all the components to make sure that everything will be working. So this takes weeks or maybe a month to finish all of these steps. So when we did the frequency measurements, this is the signal that we received with down convergence. So it's basically 0.3, right? Yeah. 0.3 was 300 megahertz. So we can have an oscilloscope to capture this. And it is pulsed. So it's basically if you're like, you know, everything is, it should be triggered, it should be like capturing the event. The event is like nanosecond, right? It's not, you don't have a like CW, whatever, like you're gonna wait for it and then they're gonna give you the signal. It's just come and go. And like if you don't have everything like synchronized, everything is triggered at the same time, you're not capturing anything. And I have a video to show you, but not for E-band frequency, for X-band BWO. So I'll show you the experiment for X-band BWO and then show you a video that we have. This is another way to radiate, is just to have an open-ended waveguide. We don't have antenna in this case. We were just trying different way of radiating the RF. Anyways, yeah, so we had an absorber before here just to make sure, and then directional coupler 20 dB, reducing the power for our BO output. So again, calibrating the absorbers to make sure that we are not sending a lot of power. Now again, like this is just showing you like to map the radiation pattern. You have to move your probe around your antenna. In low power antenna, if you guys like did any you know, antenna classes, you have your source on the table that's rotating, right? And then you're receiving the signal to map your radiation pattern, maybe 360 degrees. Here, your transmitter is like huge. It's bigger than this table and heavy. So you can't move your transmitter, the source. You need to move your receiving side. And sometimes your receiving side is a box like this, shielded. So every step you want to do is like time consuming and it requires labor work. I have 5 undergrad students doing all the labor work. And they are like doing good job, but wasting a lot of time by making a lot of mistakes. So it's compromise again, you know. Either like I'm gonna be with them all the time, which is in the basement. I saw the lab today, was very nice, window, glass. We have our lab in the basement, which is okay. Anyways, so this is basically the radiation pattern that we mapped for E-band BO. Has 3 peaks kind of, and we kind of convinced ourselves that we are radiating TM03 as we saw in the simulation. We did all the studies in design, and then we simulated using magic, and then pick code, and then we got you know, this. Then you need to integrate over a solid angle to find the total power. This is antenna field, and the total power was around 150 megawatt at 78 gigahertz. This project for DARPA was for DARPA, and they were so happy. We started, I think, with the 8 universities, 5 companies, and we made it until the last phase 1, 2, 3. We made it all the way to the phase 3. They liked the work, and they continue funding us for 4 or 5 years. And I don't know what they're gonna do with that results, but they like it. All of this is just so this one way of measuring power is not accurate. There is a lot of approximation in our field. It's not accurate. Now, the second way of measuring the power by using or by designing a directional coupler or D-dot type of. So this is the directional coupler. You can't, this is over-moded structure. Remember, over-moded means like we are not talking about fundamental mode. If you have a fundamental mode rectangular waveguide, you just Google, find a company that makes directional coupler for you, and you're gonna buy from them. They are expensive too. It's not cheap. But for over-moded, nobody makes them. You have to design them, you have to make them, send them to machine shop, and you have to make your directional coupler. You have to characterize them. Once you characterize them, you will have them in high voltage experiment or high power experiment to get your directional coupler working to measure your power, how much power you're generating. So this is for power measurement, one of them is. Now, this is one of the publication about expand directional coupler, how they design it. It's really, you need a master student or someone like doing this work for you. Every time you change the frequency, change the dimension, you need to optimize it. You need to run maybe tens of simulations to optimize your directional coupler. So, and then you need to calibrate it and characterize it. This is a directional coupler, the same one, machined and ready to be used here. This one, TM01, another design has only coupling apertures, maybe one slot aperture here. This is for K-band. Okay. So the mode of operation is higher order mode TM01 or TM03. That's TM01, it has the energy and power concentrated in a donut shape, has a null. TM03, there is 3 rings. TM02 has 2 rings of energy concentration. Let me maybe go to expand presentation and then come back to the mode conversion. I thought that they are both in the, no, they're not. So these devices are basically, what happened? I need to share. These devices are called backward wave oscillators. Do you guys want to take a break or you can continue? You guys good? Okay. So these are backward wave oscillator because, again, we go back to the slow wave structure because the interaction point between the electron beam and the electromagnetic wave has a negative slope. So that means the beam is streaming this direction and the wave is growing this direction toward your accelerator, your pulse power system. So you need to find a way either extracting the power this direction, which is done for kilowatt level, okay, but for megawatt is really gonna introduce breakdown because usually you're gonna have a waveguide here and you need to have a continuous magnetic field around it to confine the electrons. And if you extract from here, you're gonna end up with the breakdown at the window. So what we do, we reflect the signal back toward the output by having, in old days, by having a cutoff section. Cutoff section is a waveguide smaller dimension. And we have a smaller dimension is cutoff. And this is the evanescent mode, the evanescent signal I was describing, that the signal cannot propagate, so they're gonna be reflected. Or there is another way, which is cavity resonator. This cavity will resonate and reflect the same mode pattern. TM01 will be reflected as TM01, donut shape. And this is the donut shape, means like here is the concentration of energy. At the output here, sometimes they use mode converter, and it can be a periodic structure with no beam. So you stop your electron beam here, and you send your TM01 and receive it here as TE11 or Gaussian beam. Or by having the serpentine mode converters, like you curve the walls. So basically you play with the geometry to get the Gaussian beam that you require. Okay, so this is one of the main things that you need to remember or leave the the session with. It's backward wave oscillator because the group velocity is negative. The slope at this point is negative at interaction point. Okay. Another way of reflecting is using what they call Bragg reflector. And I think you guys are familiar with the Bragg reflector in other contexts, but it's basically periodic structure, right? And this is
optics and fiber optics.
yes,
Exactly.
they use Bragg reflector a lot on the small cavities. So Bragg reflector is a periodic structure. Somehow you design it by having this periodic structure. The backward wave TM01 will be reflected toward the output or toward the antenna as Gaussian beam. Okay, and this is the Bragg reflector instead of having this cavity reflector. The first problem we saw that if we have the inner radius of the Bragg reflector close to the electron beam, we start generating second frequency here, which is undesired frequency. But we did publish that anyways. We call it dual beam source, right? This is sometimes like you find an idea by accident and then you published, and other people like think it's very nice, and they did the experiment in other groups. You don't know, like sometimes like you come up with something and it has an application, but you don't know about the application. Other people, they might been searching for a solution for a while. So that's good thing about R&D, right? So this is basically then we reduce the inner radius to avoid interaction and have only power conversion for. There's a lot to describe here, but let me jump to the experimental work. So this is the hot test experiment for X-band BWO at UNM with the Sinus 6, basically. Okay, so what you see here is basically similar what you saw in the simulation graphs, basically. And now here we have to insert our Bragg reflector close to the cathode and the slow wave structure for BWO here. And we have to have everything under very high magnetic field, 2 Tesla magnetic field or higher. And that's to confine the electron beam in the axial direction, nothing in the cross section or transverse direction, because you want to have your electron to interact with only with the axial component of the electric field to satisfy Poynting theorem. I showed this before, right? So we had to have some extra coils to compensate for this because the previous experiment was using Karofnik or cavity reflector. Now here we need to have Bragg reflector, which is longer slow wave structure. So we have to have extra coils, and then we have to add more capacitors here, capacitor banks, to go to 2 Tesla magnetic field that we want. Okay. Let's see. So here's the experiment. We have our accelerator, high voltage accelerator, 500 kilovolts, 5 kiloamps around, or maybe 4 kiloamps. And this is basically what we apply at the cathode anode gap here. And everything in the strong magnetic field, as you can see. We need to monitor the voltage coming out of the accelerator, the current using Rogowski coil to measure the current. And also we need to receive the RF signal here using microwave probe. And we have to diagnose this. This experiment is expand. So we have an oscillator oscilloscope that can cover all the way to 16.5 gigahertz. So we don't have to do heterodyning and mixing the frequency down conversion in this case. So now if you run the experiment, you need to send the first pulse here to the magnetic circuit. The magnetic circuit will be discharged into this solenoid coils. These solenoid coils, and this is the magnetic circuit. This is a simplified version, of course. It has like a lot of components, but then you charge your capacitor, and then once it's charged, we fire the first trigger signal to close the SCR, the thyristor. And then this is going to be discharged. This is going to be opened, like, of course. So this is going to be discharged into the coils here. And the coils is what you see here. All the coils going to have internal resistance, of course, because they are winding wire around the vacuum tube. And this is with the first trigger, what you see here. Now you trigger your magnetic pulse and discharge, and you have to wait 3.8 milliseconds. You're actually not waiting, but the system, you have to set up your system that's gonna be having the second trigger to the accelerator after 3.8 for this experiment. For different experiment is gonna be, you have to calculate this actually. You have to send the second trigger to fire your nanosecond high voltage accelerator at this point here to have the highest magnetic field. And this is the pulse coming out of our sinus 6. This is the current and voltage signal. This is current and this is voltage. And once we send this pulse to the cathode shank, and cathode electrons will emit. Before that, you need to make sure that you have 10 to the minus 5 tours of vacuum, or maybe more, just to make sure that you have the right environment. So now this electron beam will go through this low wave structure, will generate RF, go back here, reflect, transform the mode to TM01, and you're gonna receive it. All of this is just like flash, nanosecond scale. And this is the RF signal that we receive at one of the oscilloscopes. You have to have the FFT for this in order to check your frequency of generation. Okay, I think this is a good point that I show you the video for the pulse. This is one mode, and then I'll show you that this is this mode, and then we can maybe show you a different mode pattern. Okay, ready? Now we just charge the capacitors for the magnetic circuit. It's charged, and they are ready to fire. And when they fire, basically the first trigger will discharge the capacitors for the magnetic circuit. The second trigger will be going to the accelerator to discharge the accelerator for the diode, and then the electrons will go, all this event in nanosecond, right? and I was behind the wall holding my phone and waiting for the signal. So first of all, I need to locate, because if it's dark, you don't know, like you might like even blink and then you think you saw something, right? Because it's very fast. So you need to locate your neon bulbs, and this is what I'm doing here with the flashlight. And then once I'm confident I'm directing toward the neon bulbs, I turn off the lights and start my small video clip to measure the RF. And this is what you see here. Do you see it?
Yeah, no,
Very fast. This is
one more.
one more. So this is what mode is this? Can you tell?
You can slow it down.
I want you guys like to. Yeah, I can't stop at the right moment. How to slow it down?
Yes. What's it? Wow. Oh, yes.
So this is basically 1.5 meter away from the antenna. So the light, the bulbs will light up. And now, you know, what I did, if you, anyways, what I did,
What you used?
I removed some of these new bulbs just to locate, and then I go like physically to measure where is the null. Is it on axis or not? So I removed a couple of these new bulbs. Some of them, they don't light up. Maybe they are bad, or maybe the mode's mixing. Who knows? Like, there's a lot to think about, you know. So you do the measurements many times, and every time you improve and you see, you come up with the conclusion.
And you use just ordinary neon bulb?
This is for first step for diagnostic. Yes.
The kind of bulbs is asking.
What kind?
Yes.
I mean, like you just a small ones. I don't know. Like there is no kind. So if you Google new bulbs, you're gonna find like the smallest ones.
So neon bulbs or what?
Yeah, new bulbs. Yes. So there is no. I don't think there is different types. So there's a new bulb, and they have two terminals. So basically, the RF is strong enough to light up these, to glow them from a distance. And so the RF is stronger than the threshold that new bulbs. So this is kind of a TM01. We were happy when we saw this radiation pattern. I can show you. So every day, like this changes, the same device. It's really challenging, but let me show you another radiation pattern.
Did you say the distance between the antenna and the 5.5?
1.5 meter. Yeah, 1.5 meter. 1.5 meter. We're not, maybe we are in the far field. Yeah, maybe, but like we are not, you know, in a good distance away. So it depends on the antenna. One of the antennas, we are not in the far field. And so we might like measure the side lobes as well. But our new bulb is not that big to capture side lobes of the antenna. So here, I think I have this here. Ready? One more time, huh? So this is definitely, there is a mix mode. Now this is the same device. Can you guys guess why it's a mix mode?
It seems to be differential.
Same slow stage. And probably same voltage. So the voltage, so the problem is high voltage, like they've like you attenuate a lot to measure the signal. So if you have your pulse on your oscilloscope, this is probably like 3 or 4 volt or something, as attenuated, let's say 5 volt, attenuated from 500 kilovolt to 5 volt. So even small noise that someone like is measuring here, the top of the small noise of the pulse, or like lower or in the middle, will be like 50 kV difference, you know? So you don't even know, like, are you like having the same exact voltage, or like is varying, like there's different values. So this is like a lot of challenges in high voltage experiment. And also we haven't calibrated our diagnostic for sinus for probably 15 years or 20 years, and probably need to be calibrated every year. And also, like when they come up with the calibration tool, sometimes like the calibration tool need to be calibrated with the other reference. So it's really complicated process. The good thing is in high power microwave, we're not precise. We need a lot of power at high frequency, and we can do it. And this is what the people like funding us for, you know? How can you get like more power? How you can get higher frequency? They never say like, we need a precise phase, or we need the, you know, high power, and like you can tell them like 300 megawatt, they will say it's good, high power. And when they do the experiment one more time with a precise tool, they might find 500 megawatt, you know, higher than what we measured. We just have a conservative measurement all the time. Now for this one, it's basically beam alignment. The electron, that the cathode is not very well aligned with the slow wave structure. So it's a little bit off axis. So we had this, and we changed nothing. The next day, we probably can get 200 shots a day with this machine, single shot operation. So next day we came, and then they start doing experiment. They sent me this photo. They said, we have different mode today. It's like, what happened? So every time you fire your magnet, everything is shaking. It's like a lot of voltage. So everything is like moving. So if you don't have the flanges tight enough, they might like slightly, you know, misalign each other. Slightly, even like with the 1 millimeter can make a difference in this context. So this is very, very difficult to you know, but still, this is 1 or 1.5 meter away. We still have a lot of power, even though mixed mode. And if you go to FFT for this signal, you might even like find most of the power with one frequency. The second frequency is just competing, but still like lower than the main frequency. So it's really very interesting. So let me go back to the mode conversion and show you some variety of the mode converters people have designed. I think I showed you one of two of them. Go here. Question? Yes.
RLCC, should that be used 5 for as a solution?
Yes, thyristor SCRs.
Better 5 than 4?
Okay, yeah, so that's good question. So we need to step back and talk about pulse power side of the system. So basically, this is a Tesla transformer. I think I described this roughly before. So basically, we have a step up voltage, right? So for the primary capacitors that charges the single winding for the primary winding, this is 300 volt, lower voltage side. So 300 volt, you have a thyristor over there that you can switch it to fire your accelerator. Not once you fire it, 300 volt will be stepped up to 600 kilovolt with the 1 to 3,500 turns. transformer. And now everything else will be like, you can't use thyristor. You can't, because this is the high current, regime, high voltage regime. And the thyristor cannot handle that. Any solid state cannot handle that. Only switch that we use is spark gap switch. Spark gap switch is basically 2 electrodes with a certain distance, with a certain geometry, and we put it under some pressure. And we control the pressure. And this is what we do. This is okay. Your question leads me, maybe I can show you the machine, and we had a problem once, and then I will show you, and then I come back to the mode converter. That's not a problem. What did I put that? Okay, I found it finally. So this is our sinus machine. This very nice cartoon. So basically, you have here the primary capacitor C1, and this is the thyristor. And then the primary winding is 1 turn, and I think Artem described this in more details first Monday. And this is 3,500 step up transformer. And once you fire your thyristor, the signal will come from the primary to the secondary, and then comes to this spark gap switch. This is a spark gap switch under pressure, under a nitrogen pressurized switch. And this whole thing is in oil, transformer oil insulation, because we are talking about high voltages. Transformer oil will be good insulation. Now the signal will come here, and then will go to the transmission line, and this is another transformer oil. Every time you change from one media to next, you have to have an interface. This is called membrane 1, and this is another interface, and this is oil vacuum interface, and then this is vacuum. Okay, so this is the detailed view for this. It shows you the primary winding is this one, and the secondary winding is this guy right here, which is this guy. We charge these from the prime power from 3-phase to 300 volts, and then you send your, there is I think the thyristors are here. You send the first trigger to discharge this in the primary, and then things will just follow. Here's the spark gap, and then transmission line, and then to the vacuum diode here. Okay, so one time we had to open the spark gap switch. This is spark gap switch. This is the Russian machine. It's really not fancy, but been working since '92 with nonstop. Once we start having a bad jittering, the signal is not jumping around, and we thought that there is a problem here in the spark gap, that we have an oil leaked. And the reason why, if you take a look here, this is the spark gap, okay? And this is the spark gap from other view. This is oil, and this is nitrogen pressurized gas, and this is how we measure it. In order to have the pressure on both sides of the membrane balanced, the equilibrium, we need to pressurize the oil tank as well. So we need to pressurize the oil tank and the switch. So there is what you see here, this is tube going from the oil to the spark gap. Now, if you reduce the pressure, the oil, the things will start expanding. The oil starts going up. So we had a student, he just reduced to atmospheric pressure Friday, and he went home. For some reason, he was changing, and then he reduced close to atmospheric pressure, and the PI idle came Monday morning, and he found like all the oil like leaking. So the system expanded, and the oil was leaking, and it came to the spark gap. So we had to open it to clean it, and we opened it to clean it, and this is what we cleaned the oil here, and we put it back, and it worked just fine. And this machine is really amazing. There is another machine. This is called some version of Sinus 6. It's a Russian machine. There is another machine that's more powerful. It's called Sinus 7. And if someone can buy it, I don't think they sell it to anyone. But if you can buy it, that's really very powerful machine. Higher rate, higher voltage, bigger pulse, and based on Tesla transformer. I don't think there is too many people in the world can make that type of technology. Okay, now we open the system. So since the oil was leaking, so we have the oil more than what we can handle with atmospheric pressure. We have only for this tank. This is the tank. We have only one inlet here. This is the inlet that we can add or reduce the oil. So we reduce the transformer oil from here, and in the level that we can open the spark gap. And once we cleaned it, we put it back together. We need to add more oil to the tank. There is no way to add more oil if you have only one inlet. Any idea how to do that? How to add more oil to a tank?
Pressurized.
Yeah, with the negative pressure, right? So we had to do vacuum this tank and have this inlet to kind of suck the oil in. But when we are doing this, we start boiling the oil. You see it? Because negative pressure, reducing the pressure, temperature raises. So that was like very, very crazy task. And I asked, so this is the graph. This is the problem. When you have people like okay, get the graph and I will do it, and then you come like next day and they are doing it in a way is different than what we told them. Like we told them like not to use the vacuum pump directly here, but to use maybe another tank. Yeah. So they didn't do it. They have like the maybe 25-30K vacuum pump was destroyed during this process because the oil start boiling and start sending some drops to the vacuum pump, and we destroyed it. But we could, just put the system back to work. This is another problem was for the membrane. So this is like showing you the spark gap side of the circuit of the accelerator. Yeah, this is another problem happened, maybe like since I'm talking about the pulse power. Another problem that since we are building castle around the tube with the lead bricks to absorb the X-rays, so we build around the vacuum tube, we put the lead bricks, and then we put a plate, and then we add more lead bricks. So one student was like lazy that he didn't want to continue like building the lead bricks. He put the plate close to the terminals. They're not touching, but they're close to the terminal of magnetic coil. This is 3 kilovolts. 3 kilovolts is not high, but still like jumped from the terminal to this plate, and we had a short, and then we damaged some parts of the magnetic circuit. And this is the whole 3 kilovolt, 200 or maybe 150 amps did to a plate, to a stainless steel plate, I think. Okay, what I have here. I think this is, I talked about this part. Yeah, this is another fancy way of getting the TM01 mode with a more advanced tool than the new bulbs. One thing that I did not mention, that why I'm operating my FlexBand BO at 2 Tesla, it is because we are avoiding what we call cyclotron absorption. At some specific frequency, your electrons start doing cyclotron motion. And at this cyclotron frequency, you are, instead of extracting energy from electrons, RF, it's basically you're giving back to the electromagnetic, to the electron beam. And this is gonna be having no generation. And this is the region of cyclotron absorption at expand, it's around 1.2 Tesla. And you can notice that there is no generation. So below that, you can have RF generation. Above that, you can have RF generation. And also, this is, extra information. And one of the things that I mentioned, that if you have the Bragg reflector close to the electron beam, you are generating second frequency. Basically, you're radiating 2 frequencies instead of 1. And this is the interaction point for each frequency with the slow wave structure dispersion curve. Okay, any question about this? Yesterday, I think one online student asked about if I want to have a magnetic field on the plasma of the cathode. He want to trap the plasma by using different magnetic field, and they call magnetic field decompression. And sometimes they do that by having different solenoid coils, and you can control. This is easy to do like this way, but if you have a circuit and you want to change the current from each, this is a pulse, 3 nanosecond or 6 nanosecond pulse, high voltage. The circuit need to be modified in order to have such a scheme. Now, if you have 3 times the current, you're going to have this behavior. The electron beam will change their path. And this is, in simulation, can be done, but in experimental world, it's really difficult to do. So by having this, if you can control the gap between the interaction region or the slow wave structure and the electron beam, so you're reducing the interaction here. If you change this, you can either generate 1 frequency or 2 frequency. This is what you see here is frequency time plot. So over the pulse duration, how your frequency changes. So it's going to be jumping from 1 frequency to next. And if you have the source, you can, if the first frequency is not helping, stopping maybe drone or something, maybe you change the magnetic field and generate the second frequency. And that way you're going to have the power going to either 1 frequency, or maybe at the end you have 2 frequencies competing. So you divide your energy over 2 frequencies, and you see your luck. Are you going to couple to some electronics or not? So this is one of the work we have done before. Yeah. We did that study in simulation, of course, because experiment is very expensive to do that one. You guys want to take a break?
Okay.
Okay, let's have a 10 minutes break and then, or 15, and then come back to the thing.